Okay, we are in section 9.4, talking about vector properties, how to draw them, how to do various calculations with vectors. You're going to see a lot of the formulas here are mentioned all over again from sections 9.1 through 9.3. They're just called different things. They have different terminology associated with them. So basically, a vector is a quantity that has magnitude and direction. So magnitude refers to the length of what you guys have been calling the terminal side since chapter 6. And it also has a rotation. You've been rotating since chapter 6 as well. A theta associated with it. And together these two quantities represent the entire vector. The symbol that they're going to be using for vectors is written right here. Just a little arrow that looks like a ray. Here's a little bigger version of that. And sometimes they just put a single arrow on it like that, but some books actually write it like this. But this is also a way, just a one-sided arrow. The vector OP means that the initial point, which is where it's has the dead end point, is O, if that's the first letter mentioned, and then it goes off through P and off into infinity. If it's called PO, then that means P is the initial point, and then it goes off through O and to infinity. There's two vectors here. When you're adding vectors, we call the sum of the vectors the resultant. Okay, so the resultant is just a new terminology for the word sum when you're summing two vectors together. And then some of these are just properties of vector arithmetic. When you take a vector and add the opposite vector to it, we get what's called the zero vector. The scalar product is the scalar k, which is just a regular number, not a vector. There's a difference between a vector and a scalar. A scalar is a regular number that does not have direction, whereas a vector has both direction and magnitude. So just some terminology on page 1. We get to page 2. You're actually going to start with the drawings. Again, we're going to revert to the parallelogram method in order to pick the pictures. You can follow along with me on your outlines that I included for you. We're trying to pick the vector that goes with the picture that you have. So in this picture, I know it's not very big, but basically you have let's see, now in this picture, all they want is for you to find the opposite of B. So if you have a vector that goes like this, and you want the opposite of B, all you have to do is follow it in the opposite direction. So this might represent B. This is going to represent the opposite of B. Okay, so there's only one picture that can possibly be. Choice B. Okay, then in number 2. Number 2, you're given two vectors and you're being asked to sketch the resultant, the sum of the two vectors. Okay, so with the little pictures of these vectors that they would like you to add together, you can just kind of do a makeshift sketch here. A is almost vertical with a slight bit of slant on it. So let's say this represents A. B is more like this. And then what you can do is the parallelogram method to find the resultant. Make a line that's parallel. Opposite sides in a parallelogram are parallel. So this opposite side will kind of go on the same slant as B, and this side will go on the same slant as A. Excuse me. And then the resultant goes from the origin out to the opposite vertex. Okay, and so that picture would be that's going to be C. You have A going straight up, B at a bigger slant than that, and then the resultant going that way. Okay. Then let's go to next page, number 3. Doing the same thing. You're doing A minus B. Okay, so in this picture, you're going to graph A, which again has just a slight slant on it. Then you might want to imagine where B is. You can draw it, but then you're going to actually do the opposite of it because you want to add A to negative B. So this is how B would look. But you really want in this picture negative B, and that's what you're going to actually pay attention to in the drawing. So go back the other way. This will represent opposite of B. This will represent A, and then do your parallelogram. So you're going to do a side that's parallel to B, and you're going to do a side that's parallel to A. And then the resultant will go from the origin out to the opposite vertex. Okay, so let's see which one. We already have this one checked off anyway. You have A going this way, there's opposite of B, and then this is your resultant. So D is the answer. And then here, you're being able to use the figure to evaluate A plus B. There's actually numbers associated with these. A minus B, and then the opposite of A. So all you're going to do in order to identify the vectors is basically you're going to look at the X and the Y coordinates, but you're going to put it in vector format. So this very first point that you see up towards the top of the Y-axis is at 1, 1, 4. So A is the vector 1, 4. This is called the component form of a vector. And then B is at -3, +1. And that appears, let's see, I probably have these backwards. These are so tiny. This appears to be B in the picture. That appears to be the name. And then A looks like the letter they have here, which is at -3 and up at +1. Let's just go with those. And then we're going to do these vector operations. And there's a little summary of the various vector operations down at the bottom, but you're going to see that you really don't need to memorize. These are just going to be like algebra properties that you're already familiar with. So if they ask you to do vector A and add it to vector B, then it's just the front components added together, 1 plus -3, and the back components added together, which is 4 plus 1. And there's your answer. Pretty simple. And then again, if you take A, and this I actually did these backwards, but when you're adding it doesn't matter. So this was B and this was A. When you're subtracting, it does matter. You have to put them in the order that they say. So the very first vector that they mention is A, which is -3 and 1. And then you're subtracting the vector called B, which is 1, 4. Okay, so it's like you're distributing the negative into both of these numbers. So -3 minus 1 is -4, and then 1 minus 4 is -3. And you can put that work down here if you want to. Front component minus the front component of this one, that's where that came from. And then the back component minus back component, and that's the back number. Okay, then opposite of A just means the A vector, -3, 1, times -1. And moving on to number 5. Given the vectors u and v, you're going to do more algebra on the vectors. You're going to find 7 times u plus 3v, and v minus 3u. So part A, 7 times the u vector and by the way, you can write this in the IJ form. I would be the term in the front, J would be the term in the back when you're talking vectors. And so if you wanted to write it in component form, you don't write the I and the J, but the I is like the X component and this is like the Y coordinate. And then you'd had no J component, so it would be 0. So you can write it like that, but you can also write it like this. And when you're doing 7u plus 3v, 7 times 8i, which is 56i, plus 3 times v, which is 7i plus 4j. So 56i plus 21i plus 12j, which is 77i plus 12j. And you can leave it in the IJ form or you can put it in the component form. I term goes in the front, J term goes in the back. What you can think of is almost like you're plotting a point. Like this is the X and the Y coordinates. Just that when you're talking vectors or complex numbers, they often call this the A term and this the B term. It's really just the X and the Y. Okay, then when you come to finding what's called the horizontal and vertical components, in order to put this in component form, but yet you don't have it in the I and the J form because this is called component form itself. But if all you're given is a theta and the magnitude of the vector, as you see in this picture right here, then you can use these formulas. So if you want to get the horizontal component, because as I was saying, this I, they can call it A. If you were in another section, they would call it X. This can be referred to as the B. If you were in another section, it would be called Y. So the A value is the horizontal component, or what we call the front component of the vector. And the formula you see in this box above, you want to do the magnitude of the vector. That's what those little absolute value, those symbols that look like an absolute value bars, means the length of the vector, which in this case is 11. They've already given it to you, times the cosine of the theta. Okay, so we're going to have 11 here. Then we're going to have cosine of 45, taking this information right from the picture. Cosine or sine of 45 degrees is square root of 2 over 2. So your horizontal component is 11 square roots of 2 over 2. And then B is magnitude, again, of the vector times the sine of the theta. So in this case, that would be 11 times sine of 45. And as you very well know, the sine and the cosine at 45 degrees are both the same. Same sign, same everything. Okay, so when you put this in component form, the A value goes in the front, and the B value goes in the back. Just happened to match in this case. Okay, moving on to number 7. Almost finish. Okay, this problem is going to take us back to something we learned in Chapter 8 called the Law of Cosines. Because in this problem, you're being asked to find the magnitude of this resultant. This is called the resultant whenever you're adding two vectors together. But given the information that we have, I took this and made a parallelogram out of it. So the 4 that you're seeing goes right here as well as here, because you're going to see that to do this problem you can either use this triangle, which is right side up, or the one that's upside down, because they are matching triangles. And you can use either one of those to try and find this side right here. You have 60 degrees here. By the way, in a parallelogram, adjacent angles, two angles that are connected to the same side, namely this and this, are always supplementary. Adjacent angles are supplementary. That means this angle right up here at S is 120. And then the B value is this 8, which you can put here as well as here. So I'm just going to use the triangle that goes like this. There's a 120 up there at the top where S is. I'm going to be looking for this resultant. I think I'm just going to call it X, but it does represent the resultant or the sum of these two vectors, A and B. Okay, so when I go to find this, the reason that in this triangle I can't use anything having to do with Pythagorean theorem because it's not a right triangle. I can't use law of sines because you would need at least one angle and the value of the side, the length of the side that's across from it, and I don't have that. So when you're in a side angle side situation, that is law of cosines. Okay, so then the way that goes is I'm looking for X. That'll represent this A plus B. So it's side squared. And then it's going to be the other two sides, which is 4 squared plus 8 squared minus 2 times 4 times 8 times the cosine of the angle that's across from this side. So that would be 120. And then you want to look and see what's going on at 120. Particularly, you need the cosine. So at 120, that would leave you with a 60-degree reference angle, and that would make this the long leg and this the short leg. The short leg in this case, the horizontal leg, represents the cosine that we need to finish this problem. So this would be 16 plus 64 minus 2 times 4 is 8. 8 times 8 is 64. And 64 times cosine of 120, which is the horizontal leg, the -1/2. Okay, so this is going to be 16 plus 60, that's going to be 80, and then a negative times a negative, half of 64 is 32. That gets you to 112. So now you're looking at x squared is equal to 112. Take the square root, both of these, and you have approximately 10.6, which represents the length of the resultant, the length of this vector. Okay? That's your answer for that. Number 8. Find the magnitude and the positive direction angle for the vector square root of 3, -1. So the magnitude, as given in the box at the top of this page, is, you can use this, the symbol, that absolute value symbol, but it's just the horizontal component squared which is square root of 3, plus the vertical component squared, all underneath the square root. And that's, like I said, this formula that's up here in the blue box called the magnitude. So this would, underneath the square root, you'd have square root of 3 squared, that would be 3. Then negative 1 squared would be 1. And that would be 4, which is 2. Okay, so there's the magnitude. Then whenever it says the direction angle, you're using tan. You're going to find the reference angle first and then the actual theta. Okay, so let's see. It is y over x. So this is negative 1 over the square root of 3, and that's equal to, and you can just leave it like this actually. Don't really need to rationalize it, not for purposes of what we're doing, because we're looking for the angle. We just want to know what the reference angle is that's associated with this. So let's think about this for a minute. Number one, you need to be in quadrant. Let's see, where x's are positive and y's are negative. It's going to be right in there. Remember, they said do the positive direction angle, which means we have to rotate in a positive fashion rather than rotating negative. So this is your little reference angle. Go ahead and put these numbers on here so we can talk about this. But you're talking about, this is negative 1. The x is square root of 3. And if you want to just prove to yourself what kind of triangle that is, whether or not the hypotenuse is going to be double one of these legs, so that you can figure out whether or not you have a short leg and a long leg, you can do that. You can complete this by Pythagorean theorem, which would be leg squared plus leg squared, and we already have that actually, because the magnitude is this piece right here, the hypotenuse. So anyway, you see that the hypotenuse is double that. Don't worry about the negative, just the fact that this number is double the 1 means that this is the short leg, this is the long leg. The one that matters is the vertical leg, because the vertical leg is the piece that tells you what this reference angle is. Always across from the short leg would be your reference angle, 30 degrees, or in other words, pi over 6. So know it both ways, that you can call that 30 degrees or pi over 6. Anyway, if you were to rotate all the way to here, that theta does have to do with the reference angle. You could either call this 330 as your positive direction angle, or if you're talking in sixes, this would be 6 sixes. By the time you get to 2 pi, that's 12 sixes. And if you're stopping 1 6 before you get there, then this is actually 11 sixes. So either one of these answers can be given depending on what they're asking for in my lab math or my math lab, whatever you want to call it. Okay, magnitude is 2, and the reference angle either 330 or you can call it 11 pi over 6. And one more. Problem number 9. In section 9.4, we're looking for what's called a unit vector. This is the definition of the unit vector. The vector itself over they use these double bars sometimes. It means the same thing as finding the magnitude of the vector. So we saw on the previous problem that the magnitude is just a square root of the horizontal component, just the coefficient, plus the vertical component. They happen to have it in the IJ form. You just take off the coefficients, and that would be the horizontal. This would be the vertical component. So then that's going to be underneath here, 4 plus 25. That means you're going to have a 29 underneath that. So that's your magnitude, and that's going to serve as the denominator. And then on the top, that when you just see this darkened in letter, that is just a symbolic way of saying put the actual vector on the top. So you can write the vector like this. That's the actual vector we started with. over square root of 29. You can split it up and write it as your I component, and then your j component. Or you can write it like this. You can write it in this kind of form, component form. You can write -2 5 without the I and the j over square root of 29. You know that in either of these forms that you cannot give a radical in the denominator. So if you want to simplify this all the way, which you are going to be required to do, you just rationalize the denominator. So you would do that on the bottom as well as the top. So the most simplified version of this answer, if you're going to give it in the IJ style, would be -2 square roots of 29 with the I over just 29, and then you would give the j portion, 5 square roots of 29 with the j hanging off the back over 29. Likewise here, you'd have to rationalize this as well. So that would be 29 on the bottom, and then it would be -2 square roots of 29 if you want to leave it in component form, and 5 square roots of 29 on the top. So either one of those ways, either the IJ form or in component form. They'll probably tell you which one they're looking for. And then that's the end of section 9.4.